Have you ever just stood at the ocean, like totally mesmerized by that swirling mist? It just seems so random, but there's something kind of strangely beautiful about it.
Yeah, it's like nature's playing hide and seek, right?
It really is.
But like any good game, there are rules hidden beneath the surface, and that's where fractal theory comes in.
Fractals, huh? Okay, I gotta admit, math isn't exactly my forte, but I am all for uncovering hidden patterns, especially in something as captivating as mist. So walk me through this. What are fractals and how do they connect to nature?
Okay, so think about a fern.
Okay.
Each leaf is like a miniature version of the entire frond, a repeating pattern at different scales. That's the essence of a fractal self-similarity, where shapes repeat themselves endlessly no matter how much you zoom in or out. And it's not just ferns, we see it everywhere. Coastlines, snowflakes, even the branching of our own blood vessels. Nature's full of these repeating patterns.
Okay, that's starting to make sense. So who figured this whole fractal thing out?
That would be Benoit Mandelbrot, a brilliant mathematician who saw order in what others dismissed as chaos. Back in the day, his ideas were considered pretty radical. His work revolutionized how we understand complexity in nature.
I love that, a mathematical rebel. It makes me wonder how many other hidden patterns are we just blindly walking past every day?
I know, right? It really does make you think. And to delve deeper into this world of fractals, we need to meet two more mathematical pioneers, Gaston Julia and Pierre Fatou. They really explored the intricate dance between order and chaos within fractal patterns, developing these concepts we know as the Julia set and the Fatou set.
Okay, those sound pretty intense. Break it down for me. What are these sets all about?
So imagine you're looking at a coastline from above.
Okay.
The jagged edges, the inlets and peninsulas, that's your Julia set. It represents that unpredictable, chaotic side of a fractal. Now picture a smooth, sandy beach, that's your Fatou set. The area where things are stable and predictable.
So it's like two sides of the same coin. Wild, jagged cliffs versus calm, sandy beaches. Mm-hmm. And both are part of the same fractal coastline.
Exactly. And what's so fascinating is that these seemingly opposite sets are actually intertwined. They're working together to create the complete picture of a fractal.
Okay, I'm getting the visual, but I'm still trying to wrap my head around how any of this relates to mist. Where's the connection?
Okay, so think about how mist forms. Warm, moist air cools rapidly, causing water vapor to condense into tiny droplets.
Right.
That process happens again and again, creating those mesmerizing swirling patterns. While each swirl might seem random, the overall formation follows a cyclical pattern, much like the repeating structures we see in fractals.
So those swirling patterns, are you saying they're kind of like miniature versions of larger atmospheric patterns, just like a fractal?
You're catching on. It's not that every tiny detail is perfectly predictable, but there's an underlying order within the apparent chaos. And this applies to so much more than just mist, from the branching of trees to the formation of clouds. Nature is constantly playing with these fractal patterns.
Whoa, this is blowing my mind a little bit. But if I'm being honest, all this math talk still feels a bit over my head. How can someone like me, who barely passed high school algebra, really grasp these complex concepts? Is there a way to make it more relatable?
There is, and that's where artificial intelligence comes in. Imagine having a super smart friend who can explain these complex ideas in a way that anyone can understand. That's what AI can do for us.
Wait, AI can explain complicated math. Okay, now I'm really intrigued.
Okay, so picture this. Someone wanted to see if AI could explain artificial intelligence and machine learning to, say, a 60-year-old with zero background in computer science. They used an advanced AI system called Gemini Advanced 2.0 and gave it that exact challenge.
Okay, that's a pretty specific task. Did the AI pull it off?
Absolutely. It used incredibly clever analogies. For instance, it compared a traditional computer to someone meticulously following a recipe, great at following instructions, but not very good at improvising or learning from experience.
That's a great way to put it. I've always thought of computers as being super smart, but they're really just doing what they're told, aren't they?
Precisely. But then the AI contrasted that with a description of AI as a smart apprentice who learns from experience. Instead of just following a set of rules, AI can adapt, experiment, and get better over time, just like a human learning a new skill.
So if a regular computer is like a recipe follower, AI is like a chef who can adapt a recipe based on what they've learned.
You got it. And to illustrate machine learning even further, the AI used the analogy of sorting mail. Imagine a mountain of letters needing to be sorted into important and junk. You could do it manually, but it would take ages.
Sounds like my inbox. I'm already overwhelmed just thinking about it.
Right. But with machine learning, you can train the system by showing it examples of each category. Over time, it learns to recognize patterns and can automatically sort the mail for you.
So it's like teaching the AI to spot those subtle cues we humans use, but instead of explaining it with words, we're showing it a ton of examples.
Yeah.
That makes sense. It's learning by doing just like that smart apprentice analogy.
Exactly. And the really cool part is that AI can handle vast amounts of data and spot patterns that we humans might miss entirely. This ability to see patterns in complex data brings us back to fractals and how they help us understand the world around us.
Okay, bring it on. You mentioned that fractals can be found everywhere in nature. Give me some more examples.
Okay, so think about the branching pattern of a tree. From the trunk to the smallest twig, there's a repeating structure, just like the fern we talked about earlier. And it's not just the shape, the way trees grow, reaching out for sunlight and nutrients, also follows a fractal logic.
So even something as seemingly simple as a tree has this hidden mathematical complexity. That's wild.
It is, and it goes even deeper than that. Fractals are also found in the intricate patterns of coastlines, the formation of clouds, even the distribution of galaxies in the universe.
Hold on, galaxies too. Now you're just showing off.
It's true. Mandelbrot himself once said, "Clouds are not spheres, mountains are not tones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line." He recognized that nature's complexity couldn't be captured by traditional Euclidean geometry. We needed a new language to describe it, and that language was fractals.
I'm starting to see the world in a whole new way. Every tree, every cloud, every coastline, it's like nature's whispering mathematical secrets if you know how to listen.
Exactly. And speaking of secrets, Gaston Julia and Pierre Fatou were key figures in uncovering the deeper complexities within fractal patterns.
Okay, remind me again about their work. We touched on the Julia and Fatou sets earlier, but I'm still a bit fuzzy on the details.
They were working on these ideas decades before computers even existed. Can you imagine trying to map these incredibly intricate sets by hand?
No way. I can barely balance my checkbook without a calculator.
Right. Yet, they managed to lay the foundation for much of modern fractal theory. What they discovered is that within a fractal, some points behave predictably, always staying within certain boundaries. That's the Fatou set. But other points are wild, unpredictable, spiraling off into chaos. That's the Julia set.
So it's like they found a way to map out the order and chaos within a fractal. That's pretty profound. But what does it all mean in the context of nature? How does this help us understand those real-world patterns we see?
Well, for one thing, it helps us model and analyze complex systems. Remember how we talked about mist forming and cyclical patterns? Those cycles aren't perfectly predictable, but they do have an underlying structure. By understanding the principles of the Julia and Fatou sets, we can create mathematical models that capture that interplay of order and chaos.
So even though those swirling patterns might seem random at first glance, there's a hidden logic behind them.
Exactly. And the better our models get, the better we can predict and understand everything from weather patterns to the spread of diseases to, wait for it, even the potential impact of asteroids.
Whoa, hold on. Asteroids. You're saying fractals can help us predict if an asteroid is going to hit Earth? That seems like a giant leap.
It might sound crazy, but it's true. Remember, it's all about recognizing patterns. By analyzing vast amounts of data on asteroid trajectories, their size composition, and speed, AI can use fractal principles to identify subtle variations that might indicate a future threat.
So it's like giving AI a crash course in astrophysics and letting it loose on all this data to find patterns that we humans might miss. But can it really tell us if an asteroid is going to hit us or not?
It's not about predicting a specific date and time, but rather assessing the risk. Imagine those asteroids like ships navigating a vast, complex ocean. AI helps us chart those paths, identifying potential collisions before they happen.
Okay, that's starting to make more sense. But I have to admit, all this talk about asteroids is making me a little nervous.
Don't worry, it's all about being prepared, right? And the good news is that AI and machine learning are constantly evolving, becoming more sophisticated and accurate all the time. So the more we learn about fractals and the patterns they reveal, the better equipped we'll be to understand and navigate the complexities of the world around us.
Well, that's reassuring. And honestly, it's incredible to think that these mathematical concepts developed decades ago, without computers, are now being used with AI to potentially save the world from asteroid impacts.
Yeah.
Talk about an unexpected legacy.
It is remarkable, and it just goes to show that even seemingly abstract mathematical concepts can have real-world applications that impact our lives in profound ways.
Well, I'm sold. Fractals are officially way cooler than I ever imagined. But I'm curious what other applications are out there. We've talked about mist trees, coastlines, even asteroids. What else can fractals help us understand or create?
The possibilities are truly endless. Fractals are being used in everything from computer graphics and image compression to designing antennas and modeling financial markets. They're even being used in medicine to analyze complex biological structures.
Wait, medicine? That's fascinating. Tell me more about that.
Well, think about the intricate network of blood vessels in our bodies or the branching patterns of neurons in our brains. These structures are incredibly complex, but they also exhibit fractal properties. By applying fractal analysis, researchers can gain new insights into how these systems function and develop new ways to diagnose and treat diseases.
So we're talking about applications that range from the aesthetic, like creating stunning visuals, to the potentially life-saving or like advancing medical research. It's incredible how something that started as a purely mathematical concept has become such a powerful tool across so many disciplines.
It is. And one of the most visually striking applications of fractals is in the world of computer graphics. Those breathtaking landscapes you see in movies like Avatar or Interstellar, many of those were created using fractal algorithms to generate incredibly realistic detail.
No way. So those fantastical alien worlds are actually rooted in the mathematics of fractals. That's mind-blowing.
It's true. Fractals allow us to create incredibly complex and detailed images that would be nearly impossible to generate using traditional methods. And as our understanding of fractals continues to grow, so too will the possibilities for creating even more realistic and immersive digital experiences.
This is all so exciting. We've journeyed from the misty shores of a coastline to the far reaches of space, and now we're talking about creating entire worlds using the power of fractals. But I have a feeling there's even more to uncover, right?
Oh, absolutely. We've only just begun to explore the vast potential of this field. And as we wrap up our deep dive today, I want to leave you with this thought. If fractals are truly the fingerprints of nature, as Mandelbrot believed, what other secrets are they waiting to reveal?
Wow, we've been on quite an adventure exploring this world of fractals. From like swirling mist to the vastness of space. It's amazing to see how these repeating patterns pop up everywhere in nature.
It really makes you think about how everything's connected, doesn't it? And you know what else? It makes you wonder what other secrets are hidden within these intricate patterns just waiting to be discovered.
Exactly. And you mentioned that we've only just scratched the surface of what's possible with fractals. What are some of the most exciting frontiers in this field?
Well, one area that I find it particularly fascinating is the intersection of fractals and biology. Like, think about the branching patterns of our circulatory system. Or the intricate networks of neurons in our brains.
Right.
They exhibit those fractal properties, too.
So we're not just talking about ferns and coastlines anymore. We're talking about the very building blocks of life.
Exactly. And by applying fractal analysis to biological systems, researchers can gain a whole new set of insights, into how these complex structures develop and function. It's opening up entirely new avenues for understanding health and disease.
That's incredible. It's like fractals are providing us with a new lens through which to view the complexity of life itself.
And it's not just biology. Fractals are also being used in fields like material science, creating new materials with unique properties inspired by nature's patterns.
Oh, wow.
So, for example, scientists are developing superwater repellent surfaces based on the fractal structure of lotus leaves.
Wow. So we can learn from nature's designs and apply those principles to create innovative new technologies. That's amazing.
It really is quite remarkable. And then there's the artistic side of fractals. Have you ever seen those mesmerizing fractal images?
Yeah.
With those swirling colors and intricate patterns that seem to go on forever?
Oh, yeah. They're like digital tapestries, full of hidden details that you could explore for hours.
Exactly. And those images are generated using mathematical formulas. And they really showcase the beauty and complexity that can arise from just simple rules repeated over and over again. It's a great reminder that beauty and mathematics are not mutually exclusive.
I love that idea, finding beauty in the language of math. It makes you realize that there's so much more to the world than what meets the eye.
Absolutely. And as we continue to explore this world of fractals, I have no doubt that we'll uncover even more connections between art science and the natural world.
Well, I'm definitely going to look at the world differently now, with a newfound appreciation for those hidden fractal patterns all around us. Thanks for taking us on this incredible deep dive.
It's been my pleasure. And always remember, the journey of discovery never truly ends. There's always more to explore, more to learn, and more to appreciate in this intricate beauty of our fractal universe.